Welcome back. In this video we are going to talk about functions of several variables. We're going to talk about what they are, how they compare to the functions that we've studied before. We're going to discuss in detail in this video their domains primarily. We're also going to briefly talk about range. We're going to define independent and dependent variables in this context, and we're going to talk about the graphs of functions. But really we're focused on these two. These are our main points. How do I find the domain of a function of several variables, and what is a function of several variables? So let's go back just to have some contrast. Back in pre-calculus, as well as Calculus 1 and Calculus 2, you worked with functions of one variable. Typically we had y equals f of x. Just for example, I might have y equals f of x, and f of x is equal to x squared. Now, what f of x did was it took a real number in the domain of this function, took a real number in its domain, and that was a subset of the real line. So you give me a real number that works, I put it in, and then the output was another real number. So this function was pretty simple. The domain was all real numbers because I can put in any x value I want. So I take an x from the reals, and I'm going to take that particular x value and I'm going to map it to y equals x squared, also in the reals. So every x is associated with an x squared. I might write it this way, it's just a little bit simpler. X maps to x squared. Now for a function like this, y equals the square root of x, we did pretty much the same thing, only this time our domain was not all real numbers, but a subset of the real numbers. The subset this time was all positive x values, or excuse me, non-negative x values. We can take the square root of 0, we can take the square root of a positive number. So the domain is the set from 0 to infinity, including 0. And we took all of the numbers in that set and we mapped it to some real number over here. And it turned out that the domain was also 0 to infinity on this one. So f is taking a real number x in the domain, and it was mapping it to another real number, square root of x, in the range. And that range is a subset of the real line. Okay, so that's what we did for a while. Then in the last chapter we said, what if instead of taking a real number and mapping it to a real number, we took a real number and we mapped it to a point or a location in space? So in Calc 1 and Calc 2, we were going from essentially real numbers to real numbers. And then in the last chapter, when we talked about vector functions, or vector valued functions, we had some function r of t, and it mapped to usually x of t, y of t, z of t, but it worked in 2D, it worked in 3D, it worked in ND. So mapped to x sub 1 of t, x sub 2 of t, x sub 3 of t, and you can keep going all the way through x sub n of t. So what r did was it took a number in the domain, which was a subset of the real line, and it mapped it to a point, either in two-dimensional space, or the two dimensions, the plane, in three-dimensional space, or in n-dimensional space. For this function that I've written down here, we were just looking at the terminal point of that vector. So we're taking a real number and we're mapping it to a point in Rn. Remember specifically how this worked. if we are in three-dimensional space and we're on a curve C that's generated by R of t, R of t starts at the origin and points to a particular location. It might start here and end up over here. It says you are here at this time. And that location was x of t, y of t if we were in the plane, or x of t, y of t, z of t if we're in space. It actually works in n dimensions even though we can't visualize it. So that's what we did over there. When we look at functions of several variables, we're going to go the other way. So before this class, we went from reals to reals. And in the last chapter, we went from a real number t to this point in n-dimensional space. Or if we're in 3D, we took a real number t and we mapped it to x of t, y of t, z of t. So we're taking a t and we're mapping it to a location. And that's why we often think of this as a position function. It's telling us our position at a certain time. Say, okay, well, how is that even related to this next chapter? Well, see. Instead of going from reals to reals, or the reals to the Rn, to n-dimensional space, now we're going from Rn into R. We're going the other way. So functions of several variables look like this. Our function might depend on n variables, x sub 1, x sub 2, x sub 3, all the way through x sub n. And it's going to map it to another number. I'm just going to call it w. So f is taking a point in its domain. Since this is a function of n variables, that domain is a subset of n-dimensional space, and it's mapping it to a real number. Now, most of the time we're going to work with functions of 2 variables or 3 variables, but all of the math holds for as many variables as we want, as long as it's finite, as long as that number of variables is finite. If it's not finite, there's actually another part of mathematics that would describe that as well. But for our class, everything that we're doing, or almost everything that we're doing, generalizes to Rn. It's not really an example. Let's just say in when n equals 2, this is what we've got. Instead of calling them x1 and x2, we call them x and y. So I have f of xy equals z. So this is taking a point in the domain of f. So the domain is a subset of 2-dimensional space, and it's mapping it to a another real number. We actually seen functions like this already when we looked at surfaces in that first chapter. We didn't call it a function of several variables, but this is representing a surface. So we're taking points in the xy plane. So here's x, here's y, and here's z. And we're saying, okay, let's say this is our domain. For every point in that domain D, I'm going to associate it with a particular z value. So maybe this is the point x, y, and z equals 0. Well, I'm going to map that to the point x, y, and z equals f of x, y. And when I do that for all of the points in D, I might have some surface up here. Don't really know what it looks like. I just tried to give some sense that it was hovering over D. But that's the idea. We're taking some point in the xy plane and we're mapping it to a third variable. Now, We didn't talk about this much when we were discussing graphs back in Calculus 1 or Calculus 2 or even in pre-calculus. But when we graph these functions, f of x equals x squared, this is a function of one variable. Its graph is given by a set of points x, f of x. So since this was a function of one variable and it mapped from one real number to another real number, the graph lived in two-dimensional space. Over here, there is no t-axis, but this graph lives in n-dimensional space. For every t in the domain, I get some point in Rn, some ordered n-tuple. So it'd be an ordered pair, or an ordered triple, or an ordered n-tuple if I'm in n-dimensional space. But here, if I want to graph these, it's a lot like this. If I want to graph a function of two variables, I actually have to graph it in three-dimensional space. I'm going to say it lives in three-dimensional space, lives in R3, because I need one coordinate for x, another coordinate for y, and a third coordinate for z, which is given by f of x, y. Now here, my x and y are called the independent variables, because we're assuming that they can vary in any way they want. Might say, well, they don't really have a choice in the matter. Yes, I guess I'm personifying my variables. That's okay. We're just going to let those vary, and then we're going to see, okay, well, as x and y vary, what happens to z? So from this perspective, where I've got z equals this function of two variables, x and y, I'm thinking of z as depending on x and y. So the dependent variable here is z. In general, the independent variables are the input variables. Those are the variables that comprise the coordinates of your points in the domain. Or not the coordinates, but the variables for each of those real numbers in Rn that you're talking about here, for this x1 through x of n. Those are your independent variables. And the w on this side or the z on this side, that's your dependent variable. This depends on these guys. This depends on these guys. So this is a function of two variables. If I want to graph it, I would have to graph it in three-dimensional space. Now technically, if I wanted to graph a function of three variables, f of x, y, and z equals w, the graph would have to live in four-dimensional space. It would consist of points of this form. X, y, and z are our first three coordinates, and the fourth coordinate would have to be f of x, y, and z. So this graph is in R4. So I have a function of three variables. Its graph has to have it has to consist of points in R4, because I need a coordinate for the x, the y, and the z. Those are my independent variables. And I also need a fourth coordinate for my output variable, w. So the independent variables, those are the inputs. The w is the output. Okay. So more about functions of several variables. If I have w equals f of x sub 1 through x sub n, the domain of f is a subset of Rn. And the implied domain is going to be the set of all n tuples so all x sub 1 through x sub n that do not cause the three problems that we've talked about in the past. We don't want to divide by 0. And we don't want to take logs of negative numbers or 0. Not in this class. We also don't want to take even roots of negative numbers, square root, fourth root, sixth root, because those are complex numbers, and although those are fine numbers, these are functions of real variables here, and we want our inputs to be real numbers and our outputs to be real numbers. So our domain is a subset of Rn. If we're just given a function, it's defined by a formula. The implied domain is all the ordered n tuples that don't cause division by 0, that don't cause logs of negative numbers or 0, and that don't cause even roots of negative numbers. We think about what doesn't work, and then we say everything else that works, that's in the domain. We just mentioned this earlier, the graph of W lives in not n-dimensional space, but n+1 dimensional space. I need one variable, or one dimension for each of my inputs, and one extra dimension for my output. So the domain of f of xy is a subset of R2, and its graph is given by a set of points x, y, and f of xy in R3. The domain of a function of 3 variables is a subset of 3-dimensional space. So this is going to be defined for some regions in 3-dimensional space. And those are probably going to be solid regions. For all x, y, and z within some region, our function is going to be defined. If I pick out an x, y, z in that region and I substitute it in here, that's going to give me a w value. Now the graph of this one is a set of points in 4-dimensional space, but I can't really see that. We're going to have to get creative. We need one coordinate for each of our input variables x, y, and z, and we need a 4th coordinate for w, the output f of x, y, and z. So this is in 4-dimensional space. In general, we already talked about it, the domain of a function of n variables is a subset of Rn, and its graph is a set of points you've got x1, x2, all the way through xn, and then you also need an n+1th coordinate for the output. And those are in not nth dimensional space, but n+1 dimensional space. Okay, so keep that in mind, and let's look at a couple of examples. Let's find some domains. So let's say we've got f of xy equals the square root of x plus 1, or excuse me, x plus y plus 1, all divided by x minus 1. And we're just asked to find the domain. Well, first of all, because this is a function of 2 variables, the domain is going to be a subset of 2-dimensional space. So the domain is going to be the set of all points x, y in two-dimensional space such that we don't do any of these problem things. We can't divide by 0, we can't take logs of negative numbers or 0, and we can't have an even root of a negative number, not in the real number system. So I see division in this problem. I also see a square root in this problem. I don't have to worry about the logs. So let's write down what can't happen so that we can figure out what actually is in our domain. Well, I can't divide by 0, so the domain of f is going to include all xy pairs such that x minus 1, that denominator, is not 0. Can't have that because then we'd be dividing by 0. And at the same time, this number under the radical, this expression under the radical, which will represent a number once we put in a particular x and a particular y, that has to be positive or possibly 0. It's okay to take the square root of 0. We're fine with that. So this expression under the radical, x plus y plus 1, has to be greater than or equal to 0. So that is our domain, but I might want to sketch it. So if I give you this problem and I ask you to find the domain of the function, you're a huge part of the way there if you've written this down. But if I want you to sketch it, now we have to decide what this region looks like. It's in two-dimensional space. So it's going to be some shaded region in the xy plane. Well, let's rearrange these inequalities to see what we've got. If I rearrange this, getting x by itself, I see that x cannot equal 1. And over here, just because it looks linear, I've got a y to the first and an x to the first and a constant, I'm going to rearrange this linear inequality to get y by itself. So I'll have y on this side and I'll subtract the x and the 1 from both sides. So I'll have y is greater than or equal to negative x minus 1. All right, so our domain is a set of all xy pairs such that x is not equal to 1 and y is greater than or equal to the negative x minus 1. So this is a region in the xy plane. If I want to sketch it, first I just draw my region. Or excuse me, I draw my xy plane. And now I want to add dotted lines for what is not included in my domain. So x is not allowed to equal 1. So here is x equals 1. So all of the points on that vertical line are not in the domain. Now here, it says that y is greater than or equal to this. Y equals that line. Well, that's something I can graph. That's part of our domain. So let's graph that first. Well, we know the y-intercept of y equals negative x minus 1 is negative 1. So if I plug in 0 for x, I get y equals negative 1. And the slope is negative 1. So we're going to go down 1 and over 1. And then we could also go back 1 and up 1. And that's going to be another point. And it's a line, so we can just connect all those points in a straight line when we're done. That's y equals negative x minus 1. Now we're told that y has to be greater than or equal to that. Now you probably already know if it's y is greater than that, we're going to shade above. But if you're not sure, you should check. Plug in a test value. I would test 0, 0. If I test the point xy equals 0, 0 in this inequality, I have 0 is less than or equal to negative 0 minus 1. Of course, the opposite of 0 is 0. If I want to test that point to see if it satisfies that equation, I just replace the x with a 0, I replace the y with a 0, and then I simplify the inequality. And then I look at it and I say to myself, is that true or is it false? If it's true, shade the region that includes that test point 0, 0. If it's false, don't shade that region, shade the other region. Because this line separates the xy plane into two pieces. On one side of the line, y is going to be greater than negative x minus 1. On the other side of the line, y is going to be less than negative x minus 1. We just want to know which side of the line should we shade. So we plug in 0, 0, we get this, and we have 0 is greater than or equal to negative 1. That's true. So we're going to shade the side that includes 0, 0. So that's our domain. Any xy in this blue shaded region can be substituted into this function, and the y value, we're going to be able to get a y value, or excuse me, a y value, an output value out. And I've got x and y as my independent variables, so we're going to tend to think of that third variable, that output variable, as z. Now this is a subset of the xy plane. If I were to graph this in three-dimensional space, what we're talking about down here is that part of the plane where our function is well defined. And from this picture, we see that it's going to be well defined over here, this entire region, except for where x is equal to x is equal to 1. We're going to have a problem at x equals 1. Can't cross that line. But everywhere else over here is fine. Y equals negative 1 x equals negative 1 is where we cross there. When x equals negative 1, y equals 0. So I think it goes through negative 1, it goes like this. Yeah, I think that's what we see. It's a little bit hard to see in 3D. But this blue region down here is the domain, and above that, there's some surface. Above this region, I've got a surface up here, and that surface is defined by this function. Every xy in here is associated with a z value, and that z value is the height above the xy plane. Okay, and we're going to get more into that later when we talk about graphing functions of 2 and 3 variables. Okay, so that's our first domain problem. Let's look at another one. Let's say we have f of x, or f of xy equals x times the natural log of y plus x cubed. Now, again, I'm just trying to find the domain. Notice I have a function of 2 variables. A function of 2 variables has its domain in 2-dimensional space. So the domain of f is going to be the set of all xy in the xy plane in R2 such that something is true. And we have to rule out any xy pairs that cause division by 0, even roots of negative numbers, and logarithms of negative numbers or 0. Now notice, this time I don't have any division, I don't have any roots, so the only issue is that logarithm. This expression in the logarithm cannot be 0 and it cannot be negative, not for our function of a real variable right here with real outputs. Given that, I need this to be not negative, not 0, so it has to be positive. So I'm looking for the set of all xy pairs such that y plus x cubed is strictly greater than 0. That's the domain, and if I want to sketch it, it helps to rearrange that inequality. So I have y is greater than negative x cubed, and then I want to graph that. Now this is graphed in pretty much the same way as we graphed before, except this time we say, okay, y is greater than negative x cubed, so it's not greater than or equal to negative x cubed. So I have to graph y equals negative x cubed but then I have to draw a dotted line through it. When x is -1, -1 cubed is -1. -1 times -1 is going to be +1. 1 cubed is 1, times -1 is -1. And so what you get is a shape that looks like this. Hopefully you remember the graph of y equals x cubed. We multiply it by -1 and it flips it. Okay, now y has to be greater than this. I believe it's over here. That's where y is greater. But just to check, I'm going to pick a test point. I can't pick 0, 0 this time. I almost always pick 0, 0 if it's not on my curve, because it's really easy to test 0, 0. But 0, 0 is on the curve, so I need to pick a different point. So I'm going to choose this point. So x equals 0, y equals 1. So I have 1, substituting that for y, is greater than -0 cubed. Simplify. 0 cubed is 0, opposite of 0 is 0. I ask myself, is that true or false? Yes, 1 is greater than 0, that's true. So you're going to shade the region that includes 0, 1. So shade that region over here. That's our domain this time. So there is a function. Its output values are given by this. It's well defined for all the x, y in this region. You don't want to put in that negative, or x equals -1, y equals 0, because then you get the log of -1, and that's not defined in the real numbers. You don't want to put in any x, y over here. But for every x, y over here, let's say 1, 1, you plug that in. F of 1, 1 is just 1 times natural log of 2. To get natural log of 2 over there at that point. That's our z value, is natural log of 2. And you're going to do that for all of these x, y's, and we're going to get z's for every point in this region. Okay, so now let's do another one. We're trying to find and then sketch the domain. Careful here. This is not a function of 2 variables, but a function of 3 variables. So our domain this time, if I want to sketch it, is not going to be a domain in the xy plane. It's going to be a domain in 3-dimensional space, because I've got 3 input variables here, 3 independent variables and a single real number output variable. So the domain of f this time is a set of ordered triples, x, y, z, in R3. We've got the same potential problems as before. We cannot take even roots of negative numbers. We cannot divide by 0. We cannot take logs of negative numbers or 0. I notice that I've got division in this problem. I also have a root. So yeah, let's talk about the division first. If I can't divide by 0, that means this denominator cannot be 0. So 4 minus x squared minus y squared minus z squared is not allowed to be 0. It also can't be negative because I'm not allowed to take the square root of a negative number, not in the real number system. So this has to be a positive number, and that's our domain. Now to sketch it, I need to rearrange that equation until it looks like something I know how to graph. Fortunately, whenever you're sketching these, it's going to look like one of the surfaces that we studied in an earlier chapter. If I rearrange this, I get x squared plus y squared plus z squared is strictly less than 4. Now, if that was equal to 4, I hope you all remember that that is a sphere of radius 2 centered at the origin. Now I can't really draw a dotted sphere, but the sphere itself is not included. That's a surface. It's 2-dimensional. It's a 2-dimensional surface. It lives in 3-dimensional space. The question is, is the domain everything inside the sphere or everything outside the sphere? You could test a point that's outside the sphere and see if that would work. I'm pretty sure it's inside the sphere this time, but even though I know that, let's just test one that gives you the wrong answer, that tells you to shade the other region. So here's a point that's outside the sphere. So let's test xyz equals 0, 0, 3. Well, then I get 0 squared plus 0 squared plus 3 squared is less than 4. And I'm substituting that into that equation. When I simplify, I get 9 is less than 4. And that is definitely false. 9 is not less than 4. So that means don't shade this region, shade the other region. So we want to shade the region that does not include the point 0, 0, 3. So that means we want to shade inside. So the domain of F is the interior of the sphere. Not the boundary of the sphere, not the surface itself, but everything inside. It's like a ball. It's a ball and it does not include the boundary. Okay, now notice I had a function of 3 variables, so my domain was a subset of 3-dimensional space. Here I have a function of 2 variables, so it's a domain of 2-dimensional space, and on the other one that we did, it was a function of 2 variables, and it's a subset of 2-dimensional space. Now, we could have functions of 4 variables, functions of 5 variables. All of that would be fine, and it would make perfect sense mathematically, even if we can't draw it. But the same rules hold for domain. So let's say you have a function that looks like this. So let's say W, maybe W is temperature. It's a function of x, y, z, and t. Maybe your temperature formula is kind of weird, and it's got terms that look like this. Maybe that's what it looks like. Okay. Well then, the domain of W is going to be the set of all ordered, I don't know, what are they called? It's not a 4-tuple, I'm sure. All ordered, I'm going to call it a 4-tuple because I'm at a loss for words, in R4, such that we're not dividing by 0, we're not taking the square root of a negative number, we're not taking the logarithm of a negative number or 0. So according to this, well, t has to be positive, and x minus t squared, that can't be 0. And z plus 3y, that can't be 0. So I can't sketch this one, because I can't sketch a subset of 4-dimensional space. But I can still think about it. As long as x isn't t squared and z isn't equal to negative 3y and t is always positive, we're good to go. This function is going to be well defined, even though I can't graph it. You might say to yourself, when would I ever see a function of several variables? And this is an example. This particular function, I made it up, it's not a very good example. But temperature as a function of x, y, z, and t, that actually makes a lot of sense. So I might think of temperature as a function of 3 spatial positions. 3 spatial, I said positions, but what I meant was 3 spatial variables, x, y, and z, and time t. Just for simplicity, I mean, we could make temperature a function of the number of people in the room if we wanted to. We could make it a function of a lot of different things, but let's just say it's functions of x, y, z, and t. The domain for this temperature function is going to be a subset of 4-dimensional space because I've got 4 input variables, x, y, z, and t. The graph of this function is a subset of 5-dimensional space because the graph is going to consist of points x, y, z, t, and temperature, which depends on x, y, z, and lowercase t for time. So there's 1, 2, 3, 4, 5 variables there. So this is just one example. Anytime you've got a function that depends on more than one variable, you need multivariable calculus. And there are lots of functions that depend on more than one variable, lots of quantities that we might be interested in optimizing, finding mins and maxes of, that don't just look like x of t, y of t, f of x, y, or f of x equals y. Anytime you've got independent variables, so variables that aren't linked through some equation, like they need their own space, they need their own coordinate. And the more independent variables you have, the longer these ordered n-tuples become. Now we can't always graph them because we only live in 3-dimensional space. We'll try to get around that for 4-dimensional expressions, 4-dimensional or functions of 3 variables that live in 4-dimensional space. But once I get to 5D, something like this, that's beyond me. I can't graph it. Some people use color and other things in order to graph in 5D. It's not really 5D because we live in 3 dimensions. And then we've got the fourth variable or fourth dimension, which we tend to think of as time. So yeah, we can't graph these, not in the traditional sense. But all the math makes sense. If I want to optimize this, if I want to find the point where that temperature is a local maximum temperature, it's the largest temperature nearby or the smallest temperature nearby, I want a local max or a local min, I can use calculus to find that even though I can't graph this. Later we're going to learn how to find out where the temperature or which direction to go in with respect to x, y, z, and t, so that temperature is increasing as much as possible from a certain point. We can use calculus to find that. We're going to be able to use calculus to find a lot of things that we can't even graph. But for those things that we can graph, we will. So those are going to be our functions of 2 variables, f of x, y equals z. Their domains are in 2D, their graphs are in 3D. Or our functions of 3 variables. Their domains are in 3D, their graphs are in 4D, but we're going to try to get around that. So that's what's coming, guys.